So now we switch to elastic potential energy and how the work getting done actually gets stored into elastic potential energy or gravitational potential energy. Now this question concerns basically the elastic potential energy which is getting stored in a spring, right? So let's look at the question. The question says a spring of spring constant K, which is given now. So we have a spring, okay? The spring constant is given, which is 200 Newton per meter, okay? It's slowly extended from extension of 3 centimeters. So it's already extended, right, from its natural length. So this is 3 centimeter already extended. And now we are going to pull it further and we are going to extend it to 5 centimeters. So now the extension is 5 centimeters. We have to find the work done by the extending force, right? So in order to extend the spring, we must have applied some force and we have to find the work done by the extension force, okay? Earlier, we were finding the work by using a very simple formula, which was the force into displacement, right? But here the problem is at every location, the force is variable, okay? So that way we will not be able to find, but we know that the static elastic potential energy in a spring can be simply calculated by half K into delta X square, where delta X is the extension, right? So the spring was earlier extended by 3 centimeter and now further extended to 5 centimeter. The work done by the force has actually got to increase the potential energy, right? So whatever work was done by the force F, right, that lead to increase in the potential energy of the spring, okay? So using this concept, we can now simply calculate the work done by the force, okay? So I'm going to write work done by the force is going to be increase in the potential energy of the spring, okay? So we can now write the final potential energy of the spring minus initial potential energy of the spring, and we are going to simply subtract that, okay? So let's find out UF and UI separately and then basically do the subtraction to find how much is the work done, okay? So I'm going to go my UI. Let's find the UF first, so that will be easier. So half into K into delta X square, okay? So half into K is given to be 200 and the final delta X is given to be 5 centimeters, right? So 5 by 100 or 0.05, okay? So 0.05 square, okay? And UI, which is the initial, is going to be again half into K into delta X initial square, this case half into 200 into initial extension was 3 centimeters, okay? So that's 0.03 square. Now this goes to 100, that's fine. Now we can simply calculate that. So when you do the calculation, the first one is going to be 0.25 joules. The final work is going to be 0.09, right? So now we just have to do final minus initial, and that will be the work done. So 0.25 minus 0.09, okay? Let's do that. 25, that is 0.16 joules, okay? And that is for which we have already argued, that is the work done by the force, okay? So that will be our answer. The work done by the force at, which is our extension force, which caused the extension of the spring, okay? Now